Hello guys, welcome back to another video. So today, you might see that I have become God. Well, that is because I'm back in Kanpur right now, back in my college, and this is the only light in the room, and this is the only study table I have. So this is kind of the only setup I can make. Anywho, so let's get back to this video. So today let's talk about the Buffon Needle problem. So let's say you have infinite parallel lines, or let's say you're on the floor or you look at the floor of a house. If there are square tiles, then you could see that there are a lot of parallel lines. Let's say for this case that you have infinite parallel lines, and each of them are separated at 1 meter apart or L meters apart. It is irrelevant. So let's say they're separated 1 meter apart. Keep it L meters. So let's say they're separated L meters apart. Each of the parallel lines are L meters away from each other. And let's say you have a needle which has the same length as the distance between the parallel lines, L meters. And let's say you randomly drop the needle. What is the probability that the needle hits one of the lines? Now, this might seem like a rather unimportant problem right now. Like, what is the usefulness of this? But once we get to the answer, you would see how this could be used to estimate pi. Now, this might seem very vague right now, but let's get to it and see how that goes. Okay, so the Buffon Needle. Okay, so what is the idea of this? So we have infinite parallel lines which are L meters apart, and we have one needle which is also of this length L. Now we drop it. Okay, so what are the characteristics which define this needle when it falls? So our needle will fall. Let's say that these lines are parallel to our eyesight. So let's say when you're looking straight, the lines are horizontal. So this is the reference frame, right? So with respect to this reference frame, the needle has two characteristics. One, where is its center? And also at what distance, at what angle is it from the reference frame? This angle theta. And now you might see that theta can be between 0 and pi. Now why is that? Well, the angle can go from here to here. Now why can't it be 0 to 2 pi? Because that's the general set of angles which we define, because 2 pi plus 1 is equal to 1 basically. Well, because if you cross this, then it is centered around the center of the needle. So if you get pi plus theta, that needle would look the same as the needle at theta. So that is redundant. So we could basically just look at theta going from 0 to pi. Okay, and now one more thing we'll look into, which I will explain right now. So let us say that a needle falls anywhere. Now the center, let's look at only the center point and the angle theta. Now let's say we have infinite parallel lines. The center point, anywhere it falls, let's say it falls over here, or over here, or over here, or over here. It can be between only two lines, except when it falls over here at the intersection, which the case of which we will consider later. But let's say it falls between two lines. So basically, let's say that the center point does not lie on any line. So it could fall here, here, here. Either case, it will fall exactly between two lines. So all of these are, we could choose two parallel lines without loss of generality, and we could only consider that state. So we only consider this state that these are two parallel lines at a distance L from each other, and the needle lands over here. The center of the needle lands between here. So, yeah, and now we have two parameters which affect the needle. One is the distance from the bottom line from our frame of reference, and one is the angle the needle makes with our reference frame. and obviously now from the center to the end of the needle it is L by 2. Okay, now R, the distance from the bottom line, would go from 0 to L. Okay, now here is what I meant, that we could consider also the case where it hits the line, and we could choose the line where it intersects as the bottom line. So over here we could take R is equal to 0, R from 0 to L, 0 included and L not included, because if we take L, then that would go to the above two lines which you consider. And theta, we've already said, goes from 0 to pi. Now the thing is that whether they're included or not, it is irrelevant. But for this case, let's include 0. Because the probability of, it's a continuous variable, so probability of it hitting 0 is 0. And same thing, probability of it being R equal to 0 is 0. Okay, so now this is the entire sample space, and now given that we randomly drop it, we can say that this is also uniform distribution from 0 to L, and this is also uniform distribution from 0 to pi. Now what is the case when this hits, when we consider the needle hitting the line? Well, there are two cases. One is the needle hits the bottom line, where we would have to have R to be less than L by 2 sine theta. Or the other case where it hits the top line, where we would need L minus R to be less than L by 2 sine theta, or R to be greater than L minus L by 2 sine theta. So these are the two cases. It should either be this or this for our case where the needle hits the line, where the needle hits the line. Oh, I said it correctly. Okay, so now perfect. So now what do we take? Well, we can see that the needle hits either one of the lines. There is not a single case where the needle hits both the lines. So we can see that these both are completely separate events, or these events don't have their intersection of, let's say this is event A, this is event B. A intersection B is a null set. So we could basically say the probability of A union B is equal to probability of A plus probability of event B minus probability of A intersection B, which is equal to probability of A plus probability of B. Now what is the probability of event A? Well, that is the event that, well, you have to find the density of R. Well, we have f of r comma theta dr d theta, and we have R goes from 0 to L by 2 sine theta, and theta goes from 0 to pi. Perfect. And yeah, so that would be integral from 0 to pi, integral from 0 to L by 2 sine theta, and f of r comma theta. Now R and theta are independent because we can see that there is no dependence between them. So the distribution of R is basically 1 by L, and distribution of theta is 1 by pi, dr d theta. Now we do have an identity case, but we can ignore that because the limits are within the range where it is 1. So if we had L by 2 sine theta plus 2L or something, in that case we would have to only consider the case where the limits are within 0 and L, and theta is between 0 and pi. Okay, so now what do we do? Well, now let's integrate. So we have 1 by pi L is constant, so we take that out. 0 to pi, and this is L by 2 sine theta d theta. So these L's can cancel out, and this would be pi, and now integral of sine theta by 2 from 0 to pi, we can easily calculate that is equal to 1. So we can take that this is equal to pi. So the probability of event A is equal to pi. Now, well, let's calculate the probability of event B. That would be integral from 0 to pi, integral from L minus L by 2 sine theta, L, 1 by L, 1 by pi dr d theta. Again, that would be 1 by pi L integral 0 to pi L by 2 sine theta d theta, and that is 1 by pi. So the probability that the needle hits a line is equal to 2 by pi. So it is pretty cool how pi just came out of nowhere. Now, how can we use this to estimate pi? Let's say you get a lot of straight line, you take a large cardboard, draw a lot of straight lines, let's say 1 meter apart. And you take 100 1 meter needles, or you could take 100 meter long, one meter long needle and drop it 1,000 times or 100 times. Let's say you drop it n number of times on that cardboard. And let's say it hits a line, let's say k number of times. Then we have that k by n is approximately equal to 2 by pi. So you can say that pi is approximately equal to 2n by k. Pretty neat formula. Now, another interesting thing, we can also set confidence intervals, because we can see that we can define a random variable. X is a random variable where we say that it gives 0 if needle doesn't hit, and 1 if needle hits. And obviously we can see, since it's a 0 and 1, we can see that X is a Bernoulli distribution. And we also know the probability of hitting is 2 by pi. And if we drop 1,000 needles or 10,000 needles, we could see if we drop n number of needles, and we can see that this is a binomial with n and 2 by pi. Now, using this, we could also set confidence intervals of our estimation from the actual value of pi, and we could see what is the probability that pi lies within this range, which gives a very accurate estimation of pi, which is actually really, really cool. Okay, so that was that for this video. I really hope you enjoyed it. And also I wanted to let you know that there is now an Instagram account for this channel, which is called Fun with Schrodinger. So please follow that account for updates and on anything about the video or cool reels, which I might or might not upload as videos. And well, I shall see you in the next video. Like on this video, comment below, and share it with your friends. And please subscribe to my channel. Thanks so much.